So welcome back. We're going to continue from, well, we finished an example of Sidorenko's conjecture, a very special case, baby case. I encourage you to do the exercise of extending the arguments we've seen for path of length 2, or you can see it as complete graph with 1 and 2 vertices on two sides. You can extend it to any trees and complete bipartite graphs. So today we will see two more applications of Schirr's lemma. The first one, it's called H coloring. So let's see what's the first one about. Still about graphs. In Sidorenko's conjecture, let's recall. In Sidorenko's conjecture, what we do is we are trying to lower bound the number of homomorphisms from we have a fixed graph H, and we are counting the homomorphisms from this fixed graph to a large graph. Okay, we are how many sort of images of sort of subgraphs of H in G. When G is large, homomorphism density and subgraph density are more or less the same. How many copies of H in G? Today we're going to do the opposites. We're going to start with the large graph G, and we want to count. We want to maximize. So this is to minimize the number of homomorphisms that look like this. Now we got the opposites here in H coloring. And today, maybe today, I will explain why it's called H coloring. Today we're going to start with a large graph G. And count, we want to maximize the number of homomorphisms from a large graph. Well, not necessarily large, large graph to a fixed graph H. The other way. So this problem is called H coloring. Where does this name come from? Let me explain. In Sidorenko's conjecture, there's a natural motivation. We have a huge graph G, and we cared about how many appearance of H, a fixed graph. For example, triangles on K4s, what's the triangle density, K4 density in a large graph G? So it's a very, very classical problem, sort of type of problem in extremal graph theory. What's the motivation for this setup where we flip we cared about homomorphisms from large graph to a fixed graph? Well, let me give you two very special case of H, so-called this H coloring, and we will see why the opposite direction is equally natural and important. So one special case, let's look at special cases. One is, let's consider H to be what's the simplest graph we can think of? A clique. So let's think of H as a fixed size clique. Let's say it's KQ on Q vertices. Then what is, for a graph G, having a homomorphism to KQ, what it means is, remember, homomorphism preserve the adjacencies of vertices. So for any vertex in this KQ, let's say Q equal to 5 in this picture, its pre-image, so here's our homomorphism, its pre-image must be an independent set. Okay, in our graph G. In other words, we have to partition all the vertices and map it to different vertices. This is precisely a Q-coloring independent sets. It's a Q-coloring. So every homomorphism from G to KQ corresponds to a proper Q vertex coloring of the graph G. So every such homomorphism is a proper Q coloring of G. So if you want to count the number of homomorphisms to a fixed size clique, it's equivalent of saying we can get a hold on the number of proper colorings of our graph G. That's one very useful case. Good. Another very special case is that we can, for a special choice of H, homomorphisms of this type to H becomes independent sets. So first of all, let me explain why this name H coloring. Because when H is KQ, it's Q coloring, right? So for general H, that's why we adopt this name called H coloring. Now let's consider this case when H is this graph. This graph has two vertices that are adjacent, and there is a loop on one of the vertex, exactly one of them. Looks like a little bit strange choice. So let's see, what is this homomorphism from a graph G to this graph? Okay. Well, what we're going to do is we're going to look at the pre-image of this vertex. Okay. So let's take a look. The pre-image of this guy in G, what do we know? It must be an independent set. If two vertices are adjacent, they can be both mapped to here because there is a loop. So it preserves this adjacency. But it cannot be mapped here. This is not okay. So the pre-image of any vertex that's not a loop, as we said above, must be an independent set. That means every possible way of every possible homomorphism from G to this graph corresponds to each one of these homomorphisms corresponds to an independent set, a particular independent set, by looking at the pre-image of this vertex. So there is a one-to-one correspondence between the set of all homomorphisms to this graph and the set of all independent sets. So there is the set of all such homomorphisms corresponds one-to-one correspondence to independent sets in G. So I will use this notation for the set of all independent sets in G. Any questions so far? So the set of proper colorings of G, or the set of independent sets of a graph G, are among those most studied objects in graph theory. So they are both a very special case of this so-called H coloring, the homomorphisms from a large graph that we want to study to a fixed graph. So the theorem we're going to prove today, there's a very beautiful theorem that says that if you want to maximize the number of such coloring. So here in Sidorenko, we minimize homomorphism given the edge density of G. So we're going to do the same. We're going to give the density of G and ask which G maximize homomorphism to H graph, a fixed graph. Here's a result by Galvin and Etali, who proved that for any graph without multiple, for any fixed graph, it's okay to have loop, but we don't allow multiple edges. This is not okay. For any such choice of H, then the graph among all regular graphs with given degree, the KDD, complete bipartite graph, maximize the number of homomorphisms, the H colorings. Let H be a graph with loops allowed, but no multiple edges. Then we have for any n vertex deregular bipartite graph, G, the number of H colorings, which is the number of homomorphisms from G to H, is at most this guy. So what does this mean? Well, if our graph G, it's deregular, right? If it's the union if you have union of KDD and the number of such copies n over 2D, this is an n vertex graph that's deregular, disjoint union of KDD. The number of H homomorphism from this to H is basically the number of homomorphisms of KDD to H coloring, and then each one of them are independent, raised to power n over 2D. So this is saying the number of H colorings for a bipartite graph that's regular is maximized when it's union of complete bipartite graph, KDD. So this is saying for bipartite graphs, bipartite regular graphs, irregular graphs, G, the number of H colorings, such homomorphisms from G to H, is maximized when G is a union of KDD, disjoint union of KDD. So let's do the same thing as we did in the last page. We're going to state the consequence of these results in the two special cases. The case when H is a fixed size clique, so we count the number of Q colorings, and the case when H is this graph, then it counts the independent sets. So as corollary, for any m vertex deregular bipartite graph G, we have CQ of G is at most CQ of KDD to the power n over 2D, where CQ is the number of proper Q colorings. Proper Q colorings. of this graph. And another corollary, when H is a single edge with a loop, then this one was originally proved by Jeff Kahn. He counts the number of independent sets. So for any n-vertex deregular bipartite graph G, the number of independent sets can be called I of G is at most I of KDD raised to power n over 2D. Here, I is the number of independent sets. Okay. So to make things simple, rather than proving this theorem, I'm going to prove this special case when H is a single edge with a loop, which counts the number of independent sets in the graph G. The same proof, you can modify it to prove this more general case. I will leave it for you as exercise for you to try to extend it to this more general case. So now let's prove this corollary. So we're going to use entropy, and we're going to use Schur's lemma. So entropy, the cardinality of the sets we want to estimate is the set of all independent set of G. Okay, so this is cardinality of that. To give an upper bound on that, well, natural thing to do is we uniformly random sample independent sets from the set of all independent set of G. Then the cardinality is associated to the entropy of these random independent sets. Then we want to use Schur's lemma to somehow upper bound the entropy of these random independent sets. Okay, let's try to do it. We know G is bipartite graph, so let's give name of the bipartition of G. Let's call one side the odd side, the other side the even side. Proof. Let's let V of G take a bipartition. Let's say O and E, the odd side and even side, be a bipartition. Of G. First thing to notice is that these two parts is of equal size because the graph G is regular. So G is regular implies that O and E, two sides, has the same cardinality, n over 2. Okay. As usual, we're going to write I of G for the set of all independent sets. What we're going to do is we sample a random independent set uniformly from a set of all independent sets. Uniform random independent sets in G. What do we know? We then know that the entropy of X equals to, okay, let me sample one more thing and then we write everything together. Let me also sample a random, uniform random independent set from the set of all independent sets in KDD. Okay, then we know that what do we need to prove? We need to prove this thing, right? So let's derive. Our goal is I of G and most I of KDD n over 2D. Let's take log on both sides. This is the same as log of I of G is at most n over 2D log of I of KDD. Okay, Now, we sample X uniformly from I of G. Log of this is precisely the, by maximality, axiom, the entropy of X. And this is the entropy of Y. So our goal becomes proving that. So our new goal is to prove entropy of X is at most n over 2d times entropy of Y. Okay? This is what we're going to do now. To use Schur's lemma, well, we need to have a vector form for our random variable X. Well, how do we view X as a vector form? We have our graph G with odd side and even side. X is some independent sets in here of G. So if we view each vertex as a coordinate, this X is basically a subset of vertices. We can use the indicator variable for each vertex being in this random independent set or not to expand X as a random vector. So we can write xv for the indicator function of the event that vertex v lies in our randomly chosen independent sets. Then we can view X as a random vector. Okay, where we're going to write it like this, as xo, xv, xe, where xo is just the vector of all indicator function xv, where v is on the odd side, and xe is all the indicator function where the vertex is on the even side. So far, so good. We haven't done anything yet. Just rewrite how E looks like. Now, using chain rule, let's first estimate Hx. Using chain rule, we know that the entropy of X equals to, it doesn't matter, symmetric. So let's say the n equals to entropy of the even side plus the entropy of the odd side, given even side is already revealed, given that we revealed even side. Okay, so let's use Schur's lemma to do this, to bound. We're gonna use Schur's lemma. Here, how to bound this guy? Well, to use Schur's lemma, we need to, so let's draw a picture. This is the odd side, this is the even side. So here xe are the indicator functions for vertex v in E being in X or not. So the coordinates are vertices in E. To use Schur's lemma, we need to randomly sample a subset of coordinates. In other words, we need to randomly sample a subset of E. To use Schur, we use a random subset of E. We need a random subset of E, right? How do we choose a random subset of E? Well, what we're going to do is we randomly choose a vertex, a random vertex Z, and we're going to look at its neighborhood. This is going to be the random subset of E we're going to use. So this would be neighborhood of a random vertex. Oh, to be precise, this is what we're gonna do. We're gonna sample a random vertex Z on the left-hand side, the old side, and let F to be the neighborhood of Z. So this is N of Z. Okay. Now we need to estimate the probability that each coordinate is included in F. We know this graph is D regular, so this is of size D, and E is of size N over 2. So the probability, since Z is uniformly chosen, so each vertex is equally likely to be included in this set. The probability is D over N over 2. There's D of them. If you hit one of these, you are in here, right? So mu, we have for each V in E, probability of V in F, this is the mu we're going to use, is D over N over 2. Okay, now we use Scherer's lemma. That the entropy of the even side equals to, is at most 1 over mu, which is N over 2 over D, expectation over random set of coordinates, which is F, entropy of the projection to this random set of coordinates, which is XF. Okay, you look at the random projection, this is XE, now we project it to F. Okay, so what is this? This is nothing but, let's rewrite it. This is N over 2D. The expectation of F, F is the neighborhood of Z. So it's basically expectation over all choice of a uniform random choice Z. H of X, F is neighborhood of Z. So we can write it like this. These two are equivalent. Okay. Let's get rid of this expectation over Z. Since Z is uniformly chosen, this is N over 2D. Z is uniformly chosen in O, the left side, right? So each vertex has probability N over 2 to be chosen. Okay, sum over all vertices in the oxide, entropy of the neighborhood is vertex V. Okay, we get rid of the expectation. These two get canceled out. So it equals to, so we get entropy of the even side equals to 1 over D, sum of V in the outside, entropy of the projection to the neighborhood of V. Good. Now we need to look at the conditional entropy of the outside given the even side. The conditional entropy of the outside given the even side, well, let's first use subadditivity. What does it mean? Well, what's this guy? Recall, this guy is nothing but xv, v in O. Itself is a vector. So it's at most the sum of all these indicator, entropy of the sum sum of the entropy of this XV, conditioning on XE. So it's conditional additivity. This is at most sub-additivity. The sum over V in O, H of XV conditional XE. Okay? Now we're gonna do, we're gonna make it even larger. So here, this information is too, we don't need to reveal all the XE. In fact, when we have V on the off side, let me draw a picture again. This is off side, even side. This is V, right? Whether V lies in the independent set depends only on n of V, its neighborhood, not on all vertices in E. So this is so-called spatial Markov property. So that, with that being said, that means we can forget about all those that's not in n of V. But we don't even need to use that. We just need to use drop conditioning. Remember, if you drop some things in the conditioning part, you can only increase the entropy. If you know less upfront, then the information you get from random variable can only increase. So this is at most by dropping conditioning. Sum of V in O, H of XV, H and V. Okay, now we have these two. Combining these two, put it together, we have, so H of X equals to this plus this, which is at most, putting it together, 1 over D, sum V in O, entropy of X and V, plus D times entropy of XV given X and V. Okay. Just calculation. Any questions so far? The last step is to associate this. Remember our goal. Our goal is this. Where this comes. Okay. So our goal is Hx is amongst n over 2d times Hy, where y is a uniformly chosen independent sets from KDD. So that means if we can get a uniform bound, what's the number of vertices here? This set is of size n over 2. Multiplied by 1 over d is exactly n over 2d here. So that means it's enough to prove for any such choice of V on the left-hand side, if you look at this sum, it's at most the entropy of Y. If we can do that, we are done. It suffices to prove that for any V in O, H of X and V plus T times H of XV X and V is at most H of Y. This is what we're going to do. And the idea is to define a random independent sets. Define some distribution over independent sets in KDD. W in KDD. Such that, so this is the left-hand side. The entropy of W is exactly the left-hand side. This is what we're going to do. We're going to define a random independent sets in KDD whose entropy equals to the left-hand side. Then we are done. Because by maximality, the entropy of a random independent sets in KDD is maximized when it's uniformly distributed, which is Y. All right? So all we need to do now is to define such a random independent set W with its entropy equal to this. To do that, well, this is simple. Essentially, KDD. So what is this guy? The idea is basically this. Let me draw a picture. This is V. This is MV, right? So here, if you forget about D, look at here. This is entropy of the neighborhood plus, given the neighborhood, you give the entropy of V. So it's exactly the information you get from a star. What does this D means? That means if we make a IID, make copies of V, blow it up into D times. That's precisely KDD, right? And that's how we're going to define W. We're going to define W in such a way that marginally on each side, they agree with this. So here's how we define W. So the first step is the marginal distribution on, okay. Let me write KDD like this, with one side A, one side B, okay? This is my KDD. One side A, one side B. So the marginal distribution on one side, let's say B, is the same as the distribution of X and V. When you sample X, we know its projection, X and V. It has a marginal distribution there. We let W to be sampled so that its marginal distribution on B is the same as that. I.e., if you look at W projected on B and X projected on MV, they are identically distributed. Okay, then what does that mean? That means HWB equals to HXMV. Okay, second step. For every vertex U in here, its conditional entropy, condition on B, is the same as the conditional, its conditional distribution is the same as XV, conditional XMV. Cool. In other words, WU condition on WB and WV condition on X condition on these are identically distributed. Okay, so this means W, the entropy, equals to WB plus, and this is IID for every vertex U, equals to plus, they are conditional WB, different U are independent of each other. So plus D vertices in A, the entropy of WU conditional WB, right? Which is, in our definition, X and V plus D H XB conditional X and V as desired. This finishes the proof. Any question? Okay, let's review this proof really quick. We want to prove that among all regular bipartite graphs, the disjoint union of KDD has the most number of independent sets. So how we're going to do it is we associate the independent sets with the entropy of uniformly chosen sampled independent sets. Then this inequality is translated to this inequality about entropies of random independent sets, one sample from G, one sample from KDD. Now, for this entropy of X, write it as one projection on each side, outside and even side. By chain rule, split them into two parts. Using Schirr's lemma, making use of random projection, where the projection coming from the neighborhood of a random vertex Z, we can then bound the entropy of one side by this quantity, by the sum of neighborhoods of vertex scaled by 1/d. The other side, just by subadditivity and drop conditioning, we can write in a similar form. Putting together, we have an upper bound on the entropy. The very last step is to associate this thing we just defined, derived, with the entropy of some random independent set W. Then we are done by maximality. Okay. Let's take 1 minute break. We will resume in a minute. Okay, so one thing I want to mention that why we can do the second step, why we can make sure that every vertex in A, they look the same. It's because every vertex in A, they are identical. They have the identical neighborhood. So if they don't have the identical neighborhood, this is sometimes not possible to require, to insist on. Okay. So that finishes the application of Schirr's lemma for counting independent sets, in general, counting H colorings or fixed size H. The next application we're going to see, not for graphs, is for matroids. So we're going to do counting matroids. So what is a matroid? So matroid, it's a generalization, a common generalization of is an abstract generalization of vector spaces. So let me write it. A matroid is it's an abstract generalization of, so what's in vector spaces? Linear dependency of linear dependency, dependence in vector spaces. Okay, formally, it's easy to define it. It's just a pair, a matroid is a pair E and B, where E is a ground set of points. It's a finite set. You can think of it as, let's say E has size n, that's the first n elements from 1 to n. And B is just nothing but a collection of subset of E. It's a non-empty collection of subsets of E, satisfying this axiom, one axiom called base exchange axiom. What's this base exchange axiom? It's just exactly like vector spaces. If you have two bases that generate the whole vector space, what's the exchange axiom? If these two bases are different, then you can take a basis vector in one base that's not in the other. You can remove it from this base, but then you can add something from the second base to it so that it becomes a new base to generate the whole vector. And this is the axiom we're gonna take. For any B prime, which are the bases, so this is it's the basis. And then for any element B that's in one base but not in the other base, we can always find there exists an element F that's in the other base, not in the first, I keep writing this, not in the first base, such that B with E removed, but then you can add this element F from the second base, not in the first one. This new resulting set is still a base in our matroid B. Any questions about this axiom? If you think of this as a vector space, this is the collection of all bases of the vector space. This axiom holds. We will call E is the ground set. B is the elements in B are bases. And subset of bases are independent sets. Why independent? subset of a basis is linearly independent in vector space. If you are not subset of bases, we call them dependent. Okay. A subset of E is dependent if it's not independent. In some textbook, people they also define matroids as a downward closed collection of set system. This is just if you take the basis and you include all the independent sets as also elements of the matroid. These two are equivalent. I'm just taking the top level. One exercise we can prove is that given this basis exchange axiom, once again, what's a matroid? We have a ground set. We have a collection of subsets of the ground sets, which satisfy this basis exchange axiom. Given this axiom, all the bases in B, they must have the same cardinality. This, I will leave it as an exercise, not hard to prove. By basis exchange, okay. By base exchange axiom, all bases have the same cardinality. So you can also view the basis of a matroid as a uniform hypergraph, for example. And we call the rank of a matroid the size, the cardinality of any one of its bases. They have the same size. So definition, we will call it rank of a matroid EB is the size of any of its bases. This is, we call the rank. Any questions about the definition? What we're going to do is to count the number of matroids given the size of the ground set E. So let's define. Let M n R to be the number of matroids of rank R on ground set N. Maybe I should specify this, the ground set. Okay. And we're going to let Mn to be the number of matroids of any rank, all matroids on ground set N. Trivially, Mn is the sum over the number of matroids with rank R, rank from 0 to N. Okay, let's first give a trivial upper bound on Mn. What's a trivial upper bound? Well, trivial upper bound because, remember, a matroid you can identify with B, EB, right? B is basically a R uniform hypergraph. You can think of it. Well, okay, first of all, B is a subset of 2 to the e. And the cardinality of this guy is 2 to the n, right? Taking all possible subsets of a set of size 2 to the n, the number of choices of B is 2 to the n. So this implies Mn is at most 2 to the n. Or in other words, log Mn is at most n. That's a trivial upper bound. There's a lower bound by Knuth, who proved that a lower bound using log, he says that log of the number of all matroids, all n elements, is at least n minus 3/2 log n minus some constant. So there is a, well, if you take log, there's this gap here between upper and lower bound. We can slightly close this gap using a slightly more clever argument. Okay, what's the more clever argument? Observe that, in fact, B is, you can associate it, if it's rank R, then B is basically a subset of all R element subset of N. It's R uniform hypergraph, sort of, right? So B is a subset of N choose R. So that means this is of size what? This is of size, oops. N choose R, and the binomial coefficient is maximized in the middle layer, N choose N/2. Let me forget about floors and ceilings, which is up to a constant 2 to the n over square root n. So we are not choosing subsets of a set of size 2 to the n. We are actually choosing a subset of size 2 to the n over square root n if we fix the rank. So this implies M and R is at most 2 to the n over square root n, right? Implying that log MR is at most 2 to the n over square root n, implying that log M and R is at most n minus 1/2, right? Log n plus some constants. Now we can bound Mn is at most, remember, is the sum of M and R from 0 to n, which is at most n plus 1 times the maximum of M and R for all R. This is true for any R. So plugging this bound, this will be lower order term if you take log. You will get that log Mn is at most this term. Now, if you stare at this lower and upper bound on log Mn, it's off by a factor, an additive factor of log n. So the result we're going to prove today is an improved upper bound on this slightly more clever arguments. We can improve this upper bound so that the first two terms match to the first two terms of this log Mn, lower bound from Knuth. construction. So we're going to prove log mn is at most n minus 3/2 log n plus some constant. This is the theorem. We will have, sorry, I forgot to mention, we have a slight error term here. So the first two terms are the same. There is an error term of log n, additive one, using a short entropy argument. There's a more more complicated proof which can get rid of this log term with some only constant left, I think. But we're going to state this short entropy proof with improve the lower order term. So how are we going to do that? The strategy is to use entropy to bound number of matroids of higher ranks by those of rank 2. What does this mean? Well, let's first, to warm up, let's first see number of matroids of low rank, very low rank. Well, this is the number of matroids of rank 0. Rank 0 means the largest basis has size 0. The only set of size 0 is empty sets. So that means this is 1, because B has only one choice. You have to take the empty sets. This is a single one base of size 0. What's mn1? I claim that this equals to 2 to the n minus 1. Because we have to identify B, we have to choose B from non-empty subset of singletons. This is the set of singletons has size n. The total number of subset of it is 2 to the n. But we have to minus 1 because we cannot choose empty sets. So that gives us all choices of matroids with rank 1. For rank 2, we claim that we're going to use a very crude bound, but it nonetheless suffices for our purpose. Rank 2 matroids, the number of such matrices is at most n to the n. Let me first assume this claim star, or claim heart. Let's first assume this claim and then finish the proof, okay? If we assume this claim on the number of rank 2 matroids, the key lemma is the following. We're gonna upper bound number of higher rank matroids by mn2. So for any 0, at most t, at most r, at most n, we have log of number of rank r matroids plus 1 over n choose r is at most log of m minus t r minus t plus 1. So what is this? This is the number of rank r minus t matroids on a ground set of size m minus t divided by m minus t choose r minus t. Okay. If you take t to be r minus 2, in particular, taking r to be t minus 2, t equals to r minus 2, what do we get? We have log mnr plus 1 over n choose r is at most m minus r plus 2. Up there we have log m minus r plus 2. You see, we get back to rank 2, although in a slightly different size ground set. So this is a special case. This special case implies our upper bound on log mn. So let's first see how this implies the desired upper bound using this thing. Proof of the lemma implies the theorem. Well, so let's first simplify this guy. This is just computation. I'll do it rather quick. There's no math in it. So by this lemma, we know log mr plus 1 is at most n over r, you just move it to the other side, times log mn minus r plus 2 plus 1. And this by the claim, our claim is that we can upper bound the number of rank 2 matroids by n to the n. Well, here n is, there's a plus 1 here, so let me use n plus 1 to be n plus 1. So this is at most taking log n over r, choose n minus r plus 2 to n plus 1 log n plus 1. This is by the claim. Okay. Now simplify this term. We get some calculation, 2 log n plus 1 over n plus 2, n plus 2 choose r. This is just calculation. Now we use the fact we used it before. Mn is at most m plus 1 times the max of mnr for r. You add up all these, all rank, possible rank, 0 to m plus to n. So it's m plus 1 layer. We get log mn is at most log m plus 1 plus max r log mnr. Log mnr, we have a hold here. Just plug it in there. But this is maximized when it's half of that guy. So this is at most log m plus 1 plus 2 log m plus 1 over m plus 2, m plus 2, m plus 2 over 2. Okay. And this, if you do the calculation, is big O of 2 to the n times n to the minus 3 half times log n. taking another log, you get the final bound. Okay. So this part is just computation. All we need to prove, assuming the claim, is this inequality, for which we're going to use the special case and do calculation to derive the final bound. So let's see how we prove this guy. Okay. To prove this, the idea for the lemma is to use Schur's lemma making use of a random contraction for the to do the projection. Where the projection comes from random contraction. So I have to let you know what is this contraction. Okay. Let's define the contraction of a matroid. First of all, let's make use of this notation, M, E, R. This is all possible choice of B, which is subset of the ground set, choose R. All possible collection of R subsets of B, which satisfy the base exchange axiom. It looks almost like the matroid. The number of rank R it looks almost like the set of rank R matroids, except that here B could be empty sets. You don't have to take anything here. So the cardinality of these sets is one more than rank R matroid. It's the number of rank R matroids plus one, the empty set. So note, this is exactly what I just said. If E is of size n, the ground set, then the size of this set is precisely the number of rank R matroids plus one. As MER contains all contains the empty sets apart from all rank R matroids. So the contraction, if we have a matroid M, EB, okay, and we have a set T, which is a subset of elements of the ground sets E, we can define the contraction contracting T give you another matroid, which we denote by M contracted by T, with ground set being all the elements with T removed, and this B contracted by T. So what is this? Where B contracted by T, you basically take all the bases which contains T as a subset and remove T from it. Okay. Here's a picture. You have, let's say, this is your matroid. It has 4 elements, 4 bases in B, in here. The red one, green one, blue one, black one. Okay? And if I let T to be, this is my T. Then there are 3 of the bases, the red, black, blue one, containing this purple T as subsets. So the contracted bases in this contracted matroid, you throw this green one away because the green one does not contain the purple subset T. You keep the other 3, but you remove T. So if this is M, then this is M with T contracted. You get here this and purple one. Okay. Any question? If you're familiar with hypergraph, well, the original matroid, it's an R uniform hypergraph. This is nothing but the link of T, basically. So if you view, let me write it. If you view B as R uniform hypergraph, then B with T contracted is nothing but the link of T in B. But if you just alternative view. All right. So by definition, well, first of all, notice that if T is not contained in any basis of M, then we have B contracted by T. The link of T is empty, right? Is nothing. There's nothing in there. Okay. Which means for any B in this collection, MER, remember this is the collection of all rank R matroids union the empty sets. And for any T subset of E, we have the contracted one lies in E with T removed and the rank dropped by T. Okay. The only reason to mention this sentence is because this set not only contains all rank R minus T matroids, also contains the empty sets. So it's possible that T is not in any of these spaces. Then we have to include this as one of the elements in here. Okay. So then our task becomes bounding the cardinality of this guy by the cardinality of this one using Schur's lemma. So now we can prove the lemma. Let E to be of size to be the first n element. And we're going to draw sample a random element from this MER. Could be the empty set or could be any one of those rank R matrix. By maximality, we know that the entropy of X equals to log base 2 MNR plus 1, the empty set choice. Now, we're going to view X as a vector form to apply Schur's lemma. How do we view it as vector form? Well, this, if you recall, is the elements in here are some R uniform hypergraph, could be empty hypergraph. So we can use indicator functions for each R set, whether it lies in B or not, to expand X. In other words, we can view X as random vector XR, where R is a R subset of E of the ground set. Okay, and XR is the indicator function for, the fact that R lies in our random X. Now, to do Schur's lemma, this is the coordinates, right? We need to randomly sample a subset of coordinates. So how are we going to randomly subset the coordinates? We're going to do it, as I said, random contraction. So first of all, let's define the contraction. For each T of size T, the contraction X with T contracted takes values in here, as we mentioned, E with T removed, and the rank dropped by T, right? So maximality, again, implies that the entropy of the random contraction is at most log of the cardinality of this size sets, which is nothing but M minus T, R minus T plus 1. This is by maximality. Okay. But what is X with T contracted on T? So here, XT is the projection of X to the set of coordinates FT, I define it, which is all those R subsets which contains T, right? If you contract it, and all we cared about is we throw away all those R sets not containing this T. We only care about link of T. So you just need to consider superset of T, which is FT here. So this is basically the projection of F onto this set of coordinates, which are superset of T. Good. Now we can use Schur. To use Schur, we're gonna randomly sample T, sample a random set of T coordinates. We're gonna do the contraction, and let Ft to be defined above. Okay, this will give us ft. Now we need to estimate for each coordinate, which is a R set in here, what's the probability that it appears in here. So for every R in E choose R, the probability that R appears in as superset of T, what does it mean? This means the probability that T is a subset of R, right? That's what this means. This equals to, we let this to be mu in our application of Schur's lemma. Well, R is a R set, contains this many T sets. So we have this many T sets that are good if we hit it, and total number of T sets is n choose T. This is the probability. If you rewrite it, you get this. I'm going to rewrite it in this form. Okay. So far, so good. We have the atom probability for each coordinate by Schur's lemma. We now have the entropy of X. Remember, entropy of X is this guy. Is at most, oops, let me do it like this, which equals to h of xr, r in E choose R, write it in vector form. Now, using our random contraction, ft, this is at most 1 over mu, so it's n over r over n minus t choose r minus t, times expectation over the projected coordinates, h of x ft. Okay. And as I said, ft depends basically on t, superset of t. And h x ft is nothing but x with t contracted. Okay. We are done now because we mentioned that by maximality, xt takes value in here. So this is true for any choice of t. So you can even get rid of the expectation, this plug in here. We are done. So I finished the proof for counting matroids apart from this claim. I'll finish the proof of the claim next time, which gives this crude upper bound on the number of rank 2 matroids. Any question? So very quickly, the proof of this. Today, what we did is counting H colorings and independent sets, and counting matroids. To count matroids, we use Schur's lemma to bound higher rank matroids by rank 2 matroids. How to bound rank 2 matroids, I haven't proved it yet, next time. So to bound higher rank to rank 2, you do random projection to reduce the rank. And the way how we do random projection, you just randomly choose a set of coordinates to do contraction and look at the link of this randomly chosen set that you contracted, that you can do the contraction. Okay. Here, it's the random contraction. Okay, if there's no question, We're going to continue on Thursday.